A researcher suspects that men, if given the chance, would lie about their heights. She suspects that they would try to say they are taller than they really are. To test this, the researcher first asks the male subjects to report their heights, and then she actually measures them. The subjects do not know they will be measured. Use the data below on a 5% significance level to test the claim that men would report a taller height than what they are in reality. These subjects were between 12 and 16 years old. Do you think this could have affected the results? Okay, we'll answer this last part at the end of the problem. But you can see first here, I've underlined this phrase because it tells us that we're supposed to conduct a hypothesis test with this data. To know what kind of hypothesis test we're going to do with this data, we have to look at the layout of the data and see if we can get any clues or hints. Okay, so it looks like what they've done here and what they described in the problem is that they took a subject and they asked them how tall they are. And then when they're done reporting their height, they then go ahead and measure the person actually to see if that height corresponds to what they reported. So there's going to be a dependency here, right? Obviously, a guy who's 5'8" is going to report a height in the vicinity of 5'8", right? Even if it's kind of far off, if it's like 5'10" or something, that's fine. But it obviously isn't going to be completely random. He's not going to try to say he's 4'11" or he's 6'7", right? If he's around 5'8", he's going to say something near there. Maybe 5'10", maybe 5'11". Maybe he'll get creative in that way. But he's not going to go too off the charts. So clearly, his reported height and his measured height is going to be somewhat connected, right? So that means this data is dependent. So the two rows of data are dependent upon one another because they basically involve data points coming from the same subject, right? A subject reports his height, then a subject is measured. A subject reports his height, then the subject is measured, so on and so forth. So this is a dependent t-test. T-test because the sample size is small, correct? So we're going to work it out by basically subtracting these values and getting a row of differences. And when we're done getting that row of differences, we're going to calculate the standard deviation for that row of differences. And then from there, we'll use that information to go on and finish the hypothesis test. So as far as calculating the standard deviation and so on, I'm going to use software in my calculator to do that for us just to save us some time. In most classes, you'll be given that value. If you have time at home, you'll of course be able to take the time to work it out. I can show you how to do the calculation for standard deviation for this particular problem, just to show you how that's done. But in general, that's provided. Like in my classes, for example, in the solutions for the problem, I report that information so they don't have to actually calculate it. They can go to the back where the answer is, get that information, and then use that in the problem. So let's go ahead and actually work out the first step of the problem, though, for hypothesis testing, which is to state the claim in symbols. So for these problems, when you're dealing with a dependent t-test, your claim is going to start out by saying the mean difference is related to the value 0 in some way. So what we want to say here is that when they look at this problem, it says that we want to look at a claim that the men would report a taller height than what they are in reality. A taller height than what they are in reality. So let's think about something real quick. If we were to actually do this subtraction just the way we see it, if we do reported height minus measured height, if we do the subtraction in that way, so this value minus this value, and if they're hypothesizing that the persons or the people being surveyed here, the men in other words, are going to say they're taller than they really are, in theory then this whole top row should be bigger than the bottom row, right? In theory. If all the men, for example, were to behave as this researcher believes, which is to say that they would say they're taller than they really are, then these reported heights would be bigger than the measured heights. And when you do the subtraction, you're going to end up with a positive set of numbers, right? Because if this number is bigger than this number, when you subtract it, you'll get a positive result. And that means that the total bottom row here, the differences, would all be positive. And if that's the case, then we're going to say the mean difference would have to be something positive, which means it's greater than 0. So that's essentially how you determine the claim. So we're saying the average difference here will be something greater than 0. Now, in problems in general, you don't have to compare against 0. Sometimes they'll put an actual number there, right? That might say the mean difference is greater than 10 or something like that. But it's typically 0, and it's very rare that a problem says anything else. But if it does, it has to explicitly say that. And our problem doesn't say that we should assume any specific difference, right? It just says that reported heights will be higher than measured heights. It doesn't say anything more than that, right? Okay, so now let's go ahead and get HA. Now, for the claim here, we look at the symbol and see that it's greater than, and that means HA is the same as the claim, right? So the mean difference greater than 0 is also HA as well as the claim. And then for HO, we have to have the opposite point of view, which of course is that the mean difference is less than or equal to 0. All right, now from there we have to get our data. Now, for this problem, the data step is actually nice. It's just n equals x bar equals s equals, right? And then, of course, you'll have a significance level typically. But when you do this, there's a little notation that we'll put with it. We say n of d, n sub d, which is the number of differences we had, x bar sub d, which means the sample mean for the differences, s sub d, which means the standard deviation for the differences. Because remember, what we're going to do is we're actually going to form a column of differences here, or a row of differences here. So we're actually going to do the subtraction of these values, just the top number minus the bottom number for our example. Okay, so I'm going to go ahead and do that for each of these values and get a solution, right? So I'm going to work that out for us. So, of course, if I were to do this all by hand, I would literally say 68 minus 67.9, and of course you don't need a calculator for that one, so you get the value 0.1, but you continue to work out all of them. What I'm going to do is I'm going to actually do all those calculations for us, fill them all in. That way when we come back, we can just get these data values. And again, in most classes, those data values are either given to you, or if it's a homework problem, you have the time to work that out for yourself for each and every value in the list. Okay, so let me go ahead and do that. I'm going to come back and report all these values. Okay, so now you see that I've done my calculation of my row of differences. So I just did the subtraction, like 68 minus 67.9 to get 0.1, 71 minus 69.9 to get 1.1, so on and so forth. I did that all the way down the line. And then what I did is I did a simple average. I added up all these values and divided by the number 12, which is how many values we had. And it gave me an average difference of -1. And then I took the numbers here in this list and I calculated the standard deviation. I'm going to have a video that will show how this calculation was done. In fact, I'll show how to do each of these calculations just to show you how that's taken care of. I think all of you can do an average, but some of you may have forgotten how to do the standard deviation in this situation. I will show you that in another video that shows where these numbers come from. It's a little time consuming, and most professors on exams don't make you do this yourself. They just provide you with this information. So either way, let's take those values now and use them to finish our problem. So the n value, of course, is 12. The number of differences is 12. The x bar for the differences is -1, right? The standard deviation turned out to be 3.5196, and the alpha from the problem is 5%. Okay, now once we have that, we're going to take those values and enter them into our test stat formula. Now, because the sample size is small, it'll be a t-test statistic, and it's more of a traditional test statistic formula than the type we've always used in the past, like when we first learned the test stat formula for the t-test. So it is basically going to be x bar for the differences minus the value you get from HO, which is going to essentially be 0 in this case. So you can say that it's going to be mu, right, sub d 0, which is going to be the value you get from HO. And then you'll have s sub d divided by the square root of n sub d. Now, this value is almost always 0. So our x bar, of course, we plug in as -1. Then it'll be minus the value you see in HO, which is 0. Like I said, it will almost always be. The standard deviation for the differences will be 3.5196 divided by the square root of 12. Okay, let's see what that gives us when we work that out. So, of course, on top we'll have -1. So we'll have -1 divided by, parentheses, 3.5196 divided by the square root of 12. And then I'm closing up that parenthesis in the denominator there, hitting enter, and with the test stat 0 or minus 0.984, right? So a very small test statistic. It's a very modest test statistic. It's pretty close to 0. Or at least, well, close to -1 standard deviations, I should say, not close to 0. But either way, it's a small test stat, and at that point, we can go ahead and probably assume that we're not going to be able to reject the null hypothesis. But to be sure, we better get a critical value, right? So let's draw our bell curve with a t-distribution. Let's take a look at our alternative hypothesis to figure out if it's a right-tailed, left-tailed, or two-tailed test. The fact that it's a greater than symbol, which points to the right, then it's going to be a right-tailed test, right? Then at that point, we'll label this, and we'll go to our table to get our critical t value. So it's going to be a t alpha value, right? Because all the alpha is going to be thrown into one tail, and that alpha value will be 5%, right? Or in other words, 0.05. The degrees of freedom is very simple. It's just this number minus 1, so the degrees of freedom will be 11. Okay, so let's look up 11 degrees of freedom under the 0.05 column on the t-table, and let's see what we come up with for a critical value. Okay, so we're looking at 0.05 and 11 degrees of freedom. We get the answer 1.796. Okay, so we found our critical value to be 1.796. And from there, we're going to make a comparison between that and our critical value. And we see that our critical value is, of course, way over here to the left. So we're going to decide that we do not reject HO. So the conclusion is that we do not reject HO. And as a result, we do not support HA. Okay, so when we look back at our claim, we see that our claim is the same as HA. So basically, it's this phrasing we're going to say, that the sample data does not support the researcher's claim, right? The sample data does not support the researcher's claim. All right, now, the last thing they ask us to talk about is, it says, these subjects were between 12 and 16 years old. It says, do you think this could have affected the results? And I guess you could come up with some rationale for it. You could say that, perhaps 12-year-olds, between 12 and 16-year-olds, they may have two issues there. One could be that, they're not being measured all the time, so they might be remembering heights that were at one time, say, shorter, and they may be reporting in their own heads a height that's taller than what they remember themselves being, but because they're still growing, it might be that their measured height is actually much closer to the reported height that they are making up, basically. The other scenario could be that at that age, they haven't yet become self-conscious about their height, and so at that point, there's not really an incentive to lie. We know that older men may lie because they may feel like it's awkward to be short, so they don't want to say that they're short. So if somebody asks them how tall they are, they'll lie and say they're a little taller than they in fact actually are. So, those could be explanations for why the results turn out the way it is. But you can see this researcher was way off the mark. Another thing that stands out in the data to me is this value here. You might wonder, if you were a researcher in the field, you might want to double check this number to see if somebody recorded it inaccurately. It seems like there's quite a difference here between the reported height and the actual measured height, and you notice that this value will have a very large effect on the overall sample mean that we get, because obviously it's a very huge value compared to the other numbers that are in the list, and it shows that the person here is actually underreporting their height by almost a foot, right? So that's a kind of a big difference, and because of that, at that point you might question whether that's actually a valid data point. Maybe somebody misrecorded it. So those are things to look out for. But at least as the data was given to us, we've answered it the way we should, and we have the correct solution, at least as far as that goes. Okay, so after this, what I'm going to do is, at the end of this video, I'm going to show you how I calculated the standard deviation for this. Actually, of course, I use software to do it to make it faster, but I'm going to show you how it could be done by hand. And that way you understand how we would come up with these values if we needed to on our own, if your teacher asked you to do that. Okay, here we're looking at how to derive these summary values here. Of course, to get the sample mean, I think that's pretty easy, and most of you understand how to do that. Once we've calculated all these differences here in blue, all we do is add them up and divide by 12 the number of values we have, and that's how we get the -1. So that's easy enough. I'm not going to redo that for us, but I will look at how to get the standard deviation. So the technique for calculating standard deviation is to create two columns. The first one will be a column of x values, which basically in this case will be the differences, and then we'll have another column called the x squared column. So we're going to write all these differences in the x column, just one by one. I'm just filling them in: minus 0.6, 0.5, negative 3, negative 1.6, negative 11.2, 1, and 1.2. All right, now what I want to do is I want to sum up that column eventually, but before I do that, I want to go ahead and square all these values. So I'm going to actually do this in our calculator. I'll square most of them. Some of them, of course, you can square in your head, but what I want to do here is just do a lot of them all at once. So what I'm going to show you is something I've done. Just to speed up the process, I've entered these into my calculator in a list. So I actually have them in my list here in my calculator. This calculator has a list called list 3, and I've entered all these differences in there already. I basically did that for us ahead of time. Now, of course, you're not going to be doing this, but you can take your time one by one to square each of them. I'm just going to accomplish that a lot faster by squaring that whole list. So I'm going to do L3 squared, and this is going to square the entire list where I have those values stored, and then I can just basically go and look at that and type them all in from there. Okay, so it's just going to make my life a little bit easier for the purposes of the video so that we don't have to spend a lot of time doing this, because mechanically you certainly know how to square values, so it's not going to be a problem. So we'll have 0.01, 1.21, 3.61, 2.89, 0.49, 0.36, 0.25, 9, 2.56, 125.44, 1, of course, and 1.44. Okay, so that's just the square of each of the values here. We just literally square them in our calculator, one after the other, until we have this whole list. Now what we want to do to calculate the standard deviation is total up those lists, sum them. So I can do that a little faster in my calculator, so I'm going to do the same thing. I'm going to come up with the sum for each of these lists. In other words, I'm going to add all these values and get the total, add all these values, get the total, and put it down there. So again, I can do this a little faster in my calculator, so I'm going to do that for us and put the answer there on the paper. Okay. So the first sum is negative 12, and for the second sum there, I get the answer 148.26, 148.26. You can see this value here, it's disproportionate effect, right? It's such a large chunk of this x squared quantity. So again, when we spoke about this at the end of the video, this number may be an outlier. It may be an accident, a mistake in the recording of the data. But either way, there it is. We have those numbers. Now from there, what we want to do is give them names. So I want you to tell me, where did this come from? So the way to name that is to say, well, this is the sum of the x column. So I'm going to actually call this the sum of x, right? And this is the sum of the x squared column. So I'm going to call that the sum of x squared, right? The sum of x squared. And at that point, let's take that and plug it into the formula for the standard deviation. That formula is equal to the square root of, it'll be n times the summation of x squared minus the summation of x, quantity squared, divided by n times n minus 1. Now, make sure all of that's under the square root, and when you're finished, take the square root of your answer and you're done. Okay, so the n is how many values we started with originally. We had 12 values. You can count that in the x column. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's the same as our n, right? Okay, so we're going to find that that's 12. And we're going to multiply by this quantity, the sum of x squared, right? The sum of x squared is 148.26 minus something squared, right? Something squared is negative 12, right? And then, of course, divide that by n, which was 12, times n minus 1, which is 11, right? So this is 132, that's 144, and then that product, and then we'll take the square root of it. Okay, so let's finish this up in our calculator then. So we'll have the square root of, I'll put it all in one thing, or you can work it out separately. Let's do it separately just to show that would be done. It's 12 times 148.26 minus, now if you square negative 12, because the negative is going to be squared with the 12, we can just put that as the same as 12 squared, right? We don't have to actually put the negative in there. So we get that, we get 1,635.12. So we'll have 1,635.12 If we multiply this, of course, we get 132 at the bottom, and then we can just divide that and take the square root. So divide our answer before by 132, then take the square root of that answer, and we have the result 3.51. So 3.5196 or so, which is the answer that we received before from the calculator, and that's what I put down on the paper. Okay, so that's how you calculate the standard deviation. It's not exactly the simplest thing to do. It's time consuming, but it isn't hard in terms of understanding what you have to do. It's just a lot of detailed work, right? And you can easily make a mistake. This is why it's better if you just retrieve that from the answer choice or the answer listing in my course. If you're working out this problem, you would just pull that number from the back where the answers are, or you would if you're in a class with another professor, you would hope that the professor has given you the S value on the exam like I do for my students. All right, and that's it.